speaker, our final speaker for this morning is Gary Birk with Tersus Environmental. He's going to talk a little bit more about chlorinated solvents and amendments and optimization of remediation.
Okay. Oh, well, thank you. My name is Gary Birk, and I've been involved with injecting carbon sources into aquifers for dealing with chlorinated solvents now for well over 2 decades. And during that period, when I first started, we just injected pure vegetable oil. From there, we went to emulsifying that using high energy shear mixers. In 2011, Tersus commercialized the use of just vegetable oil mixed with high performance surfactants to create water soluble oils that will spontaneously emulsify in contact with water. And today we're actually doing research where we can now, and have developed in the laboratory, where we can just add water and oil and create emulsions without any surfactant chemistry involved with that. So my talk today is, coming to forums like this over, 2 decades, y'all have shared with us, what some of the challenges are, like, pH issues at site, vinyl chloride, cis-DCE stall. Sometimes when we go in and we re-engineer an aquifer and optimize it, we get sapodification or making soap scum, gunk in wells. And what I'm going to share is a little bit about how to solve some of those issues and also to optimize the system. And so my talk really is going to be on, I'm going to start off with like an overview of how it works, kind of a refresher, go into ways of optimizing it, and then lastly, just touch on some of the research we're doing. In the optimization, we've developed a patented method for actually where we're doing in situ transesterification of the triglycerides. So, vegetable oils are triglycerides. They're 3 fatty acids on a glycerol backbone. And essentially now we can do transesterification of that in situ to increase the distribution of your volatile fatty acids. So when you're doing this type of project, the questions that you want to ask yourself is, how quickly do you want to close your site? And, certainly you can look at monitored natural attenuation. When you're doing those type of programs, we would encourage you to also include with that compound-specific isotope analysis, as well as adding to your program molecular biological tools. Serums here, they provide that service of doing molecular biology, and they can certainly help you with that. Moving a little bit forward, you can do biostimulation, bioaugmentation. So that's where you're adding a food source and adding bacteria to the system. And that's relatively moderate in terms of the time frame. You can add zero-valent iron to that, like they just did in this last project, where you're doing both biotic and abiotic processes. And then even faster to that would be where you would add sulfadated iron, or iron sulfide, along with the biostimulation and bioaugmentation. So in these processes, what's needed for enhanced reductive dechlorination? So really what we want to have is we want to have an aquifer that has a pH ideally somewhere between 6 and 8. The aquifer temperature ideally needs to be somewhere between 15 and 35 degrees C. There's published literature that says that the bacteria will grow fastest if you're at 25 to 30 degrees C. We often do projects after an in situ thermal remediation project when the aquifer gets down to less than 35 degrees C, and we see significant improved performance there. You need to have some sort of a carbon source that's going to ferment. Vegetable oils are commonly chosen as the amendment, and the reason is because they'll ferment to hydrogen and acetate. And also you need to have strong reducing conditions. Your oxygen reduction potential needs to be less than 100 millivolts. We have this slide at our booth, but this is a really good overview of the pathways of various chlorinated compounds and how they degrade from the parent compound down to the daughter products. And it also shows the bacteria or the cultures that are responsible for the degradation. And so these cultures are all commercially available. And once again, when we purchase cultures at Tersus, we like to purchase them from Serum. We find that they're pretty good and responsive for that. So another pathway is when, I said if you want to go a little bit faster, some of the abiotic pathways. So The nice thing about adding zero-valent iron is that's not sulfidated is you get two pathways with that. You get the biotic pathway, which is the top showing there, and then the abiotic pathway, which is the bottom. And the advantage of the abiotic pathway is we're going to bypass cis, DCE, and vinyl chloride, and we're going to go straight to those dichloroacetylene type compounds, which are very short-lived. And if you were to go and sample at a site, you probably wouldn't see that. And so they're pretty much going to go straight from the parent compound down to ethene. So let's talk a little bit about why soybean oil is used as the donor. So you can see here on the left in my slide, I'm showing this little cartoon. And you can see that there's 3 fatty acids on a glycerol backbone. And the distribution of soybean oil is primarily going to be C18 hydrocarbons. And the reason is you see the C and then the 18. So C16 means it's a 16 chain, and the 18 means it's an 18 chain carbon. 0 means that there's no double bonds in that chain. 1 means that there's 1 double bond, and 2 there's 2 double bonds in that chain. And so primarily soybean oil is going to be mostly C18 hydrocarbons, so it's a good source of hydrogen and acetate. And so the soybean oil is going to ferment through a 2-step process. So we have these long chain fatty acids are going to hydrolyze, and it's going to ferment through a process known as beta oxidation. And I'll explain where the beta comes in on the next slide. So I'm showing here is linoleic acid, which is the primary compound in the soybean oil. So this would be C18-2, and you can see the red dash double bar equal sign. So that means that's a double bonded carbon. So at the very head of it, we have the carboxyl group. And if you notice, soybean oil looks a lot like a surfactant, where it's got this head and then a long tail. So surfactants have a head and then a tail, and the head is water-loving, the tail is oil-loving, but unfortunately, soybean oil is not like that. And so the next is the alpha, and then the next carbon is known as the beta. And so that's where we have this beta oxidation coming in, because this is going to be a multi-step, two-step process. We're going to remove 2 carbons from the chain, hence beta, and we're going to release 4 hydrogens and a mole of acetic acid. And why is that important? Well, acetic acid is essential for fermentation and the reductive dechlorination to occur, and you need to have the right types of fatty acids for reductive dechlorination to occur. And so if we look at acetate, it has slow consumption. So when we inject soybean oil and it slowly ferments, the acetate is going to stick around for a considerable period of time. And the acetate will migrate some distance down gradient, a couple of meters from the injection point. And unfortunately, the acetate will stimulate PCE to TCE to DCE. But unfortunately, acetate will not stimulate cis-DCE to vinyl chloride to ethene. And for that, you need hydrogen. And hydrogen is produced from specific types of volatile fatty acids, so VFAs. And we also encourage, when you're doing a reductive dechlorination project, that you include volatile fatty acids in part of your monitoring program. And so hydrogen, though, has got rapid consumption. It's not going to stick around very long. And unfortunately, it doesn't migrate very far from the injection point. So you can inject a donor, and right around the injection zone, you're going to see complete dechlorination, because that's where the hydrogen is. But down gradient, you may see cis-DCE stall, and you're wondering why, what's going on here? And it's because in those down gradient wells, you're only generating acetate and not any hydrogen. So hydrogen is required to stimulate cis-DCE to vinyl chloride to ethene. So, and also in these systems, we've learned that pH plays a critical role in the production of volatile fatty acids. So systems that are under alkaline conditions, so that would be pH 8 or greater, enhances the activity of the fatty acid producing bacteria. And it also that we've seen at sites is that when we're under alkaline condition, we're going to mitigate or inhibit the production of methanogens. And under alkaline conditions, we get greater production of volatile fatty acids. The other issue with pH is that, the optimal pH for reductive dechlorination is between 6 and 8.5. 6.8 to 7.5 is actually the best. And generally speaking, sites that have low pH, you're going to see cis, DCE, and vinyl chloride stall. You're going to accumulate, those daughter products at your site. And so often then you go in and you want to go in and buffer that aquifer or add some type of a caustic material to raise the pH to 5. Excuse me, 7. So why is pH also a concern is that, the production of volatile fatty acids will release acids from the fermentation, and also the reductive dechlorination produces acids. So, for example, 1 mole of PCE, if we degrade that all the way to ethene, is going to create 4 moles of hydrochloric acid. So the process of doing reductive dechlorination produces acids at a site, which then drops your pH. Also, nutrients are very important to the addition to your system. And so this is a paper from that was published that I'm referencing here. And so, we found that ammonia is very important to stimulate bioremediation for reductive dechlorination. And in this paper, their study found that the addition of ammonia increased cis 1,2-DCE to ethene dechlorination 5-fold. And the addition of nutrients is really not that expensive. There's an online store called Birk that have a product called Tersus Nutrients. I think it's like less than $200 for a pail that you can then add at your sites. And it's a good source of ammonia and other nutrients to stimulate reductive dechlorination. And lastly, vitamin B12 is also a good material to add. And so, somewhere you want to be between 25 and 50 parts per billion vitamin B12 in situ in your system to stimulate reductive dechlorination. And it really doesn't take much. So I'm showing here is a photo. That's a 275-gallon tote. It's got roughly 2,100 pounds of oil and surfactant in it. And there's only 5 grams of vitamin B12 in that tote. So you can see pretty easily if there's B12 in your amendments, because it's going to be that Valentine's Day red, pinkish color. And so, it doesn't take much. It's also a good tracer, because as you're injecting it, you'll see it's like a red dye almost. So when we go in and we re-engineer our systems and we try and optimize everything, there's a possibility that we're going to create a process known as saponification. And so that's really the process of making soap. And so, the way we make soap is we take an acid and we add lye to it, and then we get this hard bar of soap. So we're injecting organic substrates that are going to ferment as volatile fatty acids, because we want that to happen. But our site's got a low pH, so we're going to inject some caustic material to raise the pH. And so in this process, we're actually going to produce soap. And so, so we shouldn't be surprised when that happens. And so I'm showing here is just some photos of samples that were sent into our laboratory to try and figure out how do we deal with this biofouling and soap scum at various sites. And so when we add nutrients, we add caustic materials, we get we're stimulating the biological growth, but we're also getting some fouling, and we're generating hard soap or soap scum at sites. And lastly, sites that have hard water. So where the natural water in your aquifer may have some calcium or magnesium. So those anions will react with the fatty acids to form this insoluble gelatinous crud at your site. And, probably 11, 15 years ago, I had this idea of injecting like milk of magnesia at sites, but it's kind of a dumb idea, because it's magnesium, it's going to react with the acids and just make soap scum. So here's an example where we've actually been treating material like that in our laboratory. And so we're involved with DNAPL projects and LNAPL projects, and often on those sites we inject co-solvents to help liberate, the NAPL. And so we tried the co-solvent with those samples that were sent into our laboratory, and it actually liquefied the soap scum. And we've also found that the co-solvents, that 1 pound of co-solvents will completely dissolve about a half a pound of vegetable oil. So it's a pretty good substrate shuttle to improve distribution of your vegetable oil in the subsurface. And then this is really cool. This is we had a client that was doing, that approached us. They were doing a groundwater recirculation system where they were injecting an organic substrate and recirculating it. And then, COVID happened and they got shut down. And so, when they got to come back to work, they had all this material in their lines and pumps, and, it kind of looks like Vaseline. And so their aquifer, it was in a karst aquifer. It was very hard water, and the aquifer had a pH of about 10. So all this, they were adding an organic substrate, fats, and that had calcium, magnesium ions in it. And while it just sat there during the shutdown, they had created Vaseline. And so they sent us samples, say, hey, can you help us with this? And so we did bench tests to see if we could liquefy this material. And we were able to add some co-solvents to that to help liquefy the material. And you can see that once that material came in contact with water, we were able to emulsify it and spontaneously and form an EVO so that it would flush out and clean out their lines and system. So now I want to talk a little bit about, so we've learned how to optimize systems and how to improve the process, but we come into situations where we re-engineer something, we improve something, but we've created a whole new set of issues. And so we've come up with a technology, and we've patented this method to do in situ alcoholysis. And essentially what we're doing is we're taking the triglyceride molecule and we're using a process known as transesterification of that in situ to release volatile fatty acids. And so we've developed two methods to deal with how to catalyze that reaction in situ. And the first one is a hydroxide-based catalyst for the transesterification of triglycerides. And they are really, we don't really like to just inject pure hydroxide. So what we do is we take the hydroxide and we react it at our production facilities with alcohols to form alkyl oxides, and we use that as our catalyst. It's easier to deal with and inject in the field, and we're also providing the alcohols necessary for the transesterification. Or we can use the biocatalysts where we're using enzymes to create the transesterification process. And so the way this process works is, so we have this vegetable oil, it's a triglyceride with 3 fatty acids on it. You're going to add some surfactants and a substrate shuttle, that co-solvent where we can take 1 pound of vegetable oil and dissolve it in half a pound of this co-solvent. And we found that we actually don't really need much of it at all because we want to just use it to help minimize any type of biofouling. We're going to then catalyze that reaction. And then by catalyzing that reaction, we're going to form a mixture of volatile fatty acids, the salts of the carboxylic acid, and then glycerol. And so what happens is we're going to break that bond. As soon as the catalyst comes in contact with the vegetable oil, that bond is going to be broken. It's going to then release glycerol, which is a soluble electron donor. And then we're going to generate those volatile fatty acids and the carboxylic acid salts. And so those are going to migrate much further down gradient than you would expect on a normal type EVO injection project. So we can also then enhance this process by, up until now, historically, maybe we've been feeding the bacteria a meal. So now with this process, we're feeding the bacteria, a meal and an adult beverage. But we can enhance the process by feeding the bacteria a hot meal and an adult beverage. And so what we want to do is, ideally, we want to heat the aquifer up to about 25 to 30 degrees C. You can do that either through a number of methods: steam hydrolysis, electrical resistance heating, thermal conductive heating. What we found best, that we've done a lot of projects now on, is that immediately after a site where they've done in situ thermal, we wait, once the aquifer gets down to 25 to 30 degrees C, then we go ahead with this process. And so really the advantage here is that, we're not producing the soap scum and all those other issues associated with optimizing your system when you do an EVO injection. And we're not really no longer relying on the dependence of EVO droplet sizes, whether it's going to be a small micron or a large micron. We're going straight to production of the volatile fatty acids that are going to generate the hydrogen that's needed to go all the way to complete reductive dechlorination. Since we've done now a couple of projects, we just did a project in Australia where we implemented this method there, and in 90 days we got 95% mass removal at the site. So it's pretty effective, and this was just without any heating the aquifer. This was just straight transesterification, the triglycerides in situ. So typical application rates, it's going to be on the oil and the surfactant, 2 to 8 grams per liter in situ. On the activator, the catalyst, ideally we want to be somewhere between, on the alkyl oxides, between 6 and 20% of the dose of the oil. And then the co-solvent, we need very little, about 0.4 grams per liter. And then often, we like to speed up the process even faster and get some abiotic reactions depending on the concentrations. And typically there, microscale zero-valent iron would be added roughly between 4 and 6 grams per liter. And then lastly, I know I'm running out of time, but our current R&D focus is on minimizing surfactants. On DNAPL and LNAPL projects, we have our surfactants down now to just 0.9 weight percent. Surfactants are pretty expensive. So we've actually now in the laboratory produced emulsions with just oil and water, where we can process that oil and water through unit operations. I'm a chemical engineer, and so we can then create oil and water mixtures without any surfactants. I'm showing here a photo of one that looks what it looks like after an hour after processing. So we also then took that processed mixture, that processed emulsion that does not contain any surfactants, and we did column studies in our laboratory where we passed it through columns and pore volumes, and then we measured the transmissivity. So we compared non-processed, just oil and water. So what I did 20 years ago, which was kind of a dumb idea and clogged up the aquifer. And you can see the transmissivity was pretty high. Couldn't pass light through it. But on the processed oil and water emulsion without any surfactants, we're down, to 3 to 5 pore volumes before, we start to see a deterioration of that material. And we're also working with, not in the environmental arena, we're doing, using surfactants for rejuvenation of asphalt. We're working with asphalt companies to provide our surfactant chemistries to rejuvenate asphalt. And we've done a couple of pilot studies on dust control in some of the Dust Bowl states where we provide surfactant chemistries to mix with oil and water to produce and minimize dust generation at construction sites. And I think I have 1 minute and 30 seconds with questions. I'm done.
Okay. Thank you very much. Thanks, Gary. I'm so unused to people being cooperative in these kinds of situations.
Well,
it's great.
You're a professor, so I got a great deal of respect,
Are there some comments or questions for Gary? There's a lot of information there. Some of you may have experienced some of it. Some of it may be new to you.
I think they're all ready for a break.
No, well, hold on. We're going to keep them here for a little bit. Okay, let me thank all of our speakers, all 4 of our speakers. There was a very good mix of I would say, academic information, scientific studies, and also practical application of that information. That's really why virtually all of you are here, is to augment your understanding of opportunities that you have to deal with the sites that you have responsibility for. So I thank all of my speakers. I thank you all for your attendance, and we'll be here for a few minutes if you want to stop up and ask some folks some questions, and otherwise we'll see you at the coffee break in a couple of minutes. Thanks very much.